Welcome back. In today's lecture I want to start with a new topic, namely collision detection. What is this all about? So, at its core, the problem comes from the representations that we have in the computer of our simulated objects. They actually don't obey volume. They don't really have physical behavior, right? If I have this cup, in reality I can hold it. I cannot just move my hand through this cup. In the computer, that's not the case. Hence, what we really want to achieve here is we want to detect whether objects actually overlap, whether they penetrate each other, and then that is typically a first step. Do they actually represent an unphysical state? And if yes, as a side task that's typically also quite crucial in practical applications, we also, for many cases, actually need distances. How far are the objects inside of each other? Where are the points that touch or intersect? This is the data that then would be processed by additional stages in order to resolve the collisions. We already spoke about this actually for the collisions of rigid bodies, right? We had a very simple collision detection and the impulse model to then change our dynamics such that we get back to a physical behavior, and there, for example, also we need the actual point of collision. So this data also needs to come out of the collision detection step. Yeah, let's take a look back. Before we had complex 3D geometries, the world in a way was much simpler. So representing objects as sprites, as shown here, and if we have a certain region with filled pixels, the pixels are either object or they're empty, like on the sides here, and then this might be an initial state, and this is a new state, and then it's pretty easy to detect by really just checking each one of those pixels. In this case, there's actually one here, on the right side of the first object that overlaps the second one. Hence, here this is actually a bad part. This is, in a way, is very easy to detect. Right. In modern games, we do not have shapes that are as simple anymore. They're not just made from a collection of pixels, and in many cases we're actually looking at 3D geometries. So how can we handle that? I also want to mention that we are looking at this from the perspective of computer games. However, collision detection is actually a topic that also plays an important role in all kinds of other applications. Here's a nice one that you can see on the slide for robotics. So this is a kind of model of a manufacturing line of a car, and what's actually interesting in this case is this green cylinder that's attached to a robotic arm. And here a quite challenging problem in practice is, how do I actually move this robotic arm? How can I move it with the degrees of freedoms that it has, such that I don't bump with the cylinder into the frame of a car, and then in this case damage both, and maybe, if I'm unlucky, even the robot, which might be really expensive. So I actually need to carefully plan to execute a sequence that does not collide with any of the geometries. And you can imagine in these cases we really want to know very exactly which parts of the real world objects would collide given a certain path or not. So this, I think, is an interesting example. Another one is this one, a medical one, from a group in Freiburg. So for medical procedures, for example, if I want to create a new hip joint or or a supplement for a bone, I actually ideally find a shape that fits with the current bones that a patient has. And then in a way we also have a geometric problem where we have a certain shape given from a scan in this case. We want to change it or add some pieces, and then given a certain range of motions, ideally this should not collide. There shouldn't be sharp edges that intersect and cause trouble when this procedure is actually done. And interestingly, also looking ahead a bit, in bioinformatics for molecular simulations, for example, it turns out that the behavior of a molecule is often largely determined by its shape, by the geometry basically that a certain chain of amino acids forms, and hence in a way figuring out the influence of a molecule often boils down to a kind of collision detection problem. How do certain molecules fit into each other? How could they interlock? And which receptor regions could these molecules fit together? So in a way, similar techniques are also important for these simulations. All right. So let me quickly recap here. This is the main algorithm as discussed in the game engine design lecture. So typically how a collision detection algorithm proceeds is by so-called broad phase. And this is kind of the big picture, looking at the whole scene typically. What needs to come out of that one is a list of pairs of objects that potentially collide. So this is not yet perfect, but in a way a first rough step to get us most of the way. So we don't need to have definite answers at this stage, but what we definitely need to avoid is having false negatives. So it may never happen that we say this pair of objects does not collide when it actually does. So we need to kind of err on the side of caution and say, right, these two potentially collide, rather than saying they definitely don't. In many of these topics, it's actually a bit of an efficiency compromise. So how much resources do I invest versus the accuracy that I get out? And by the way, what's typically called culling here in the following is to basically discard pairs of objects that don't collide. This is actually one of the important steps done in these pipelines. You can guess so. After broad phase, we come to the narrow phase. This is where we now take all these pairs that we have, and then essentially move down to the primitive level, so to the core building blocks of our geometry, and figure out, do certain triangles that I have in my geometry, do they overlap or not? It depends a bit on what primitives I have. I might also have ray and plane intersections to check for or spheres or so. But for this narrow phase, it really typically boils down to basically really computing intersections of certain primitives. And this is actually something that we won't look at in detail. By now, this has been studied in the past in a very detailed way. There are very good books and very good algorithms. It's actually quite tricky in practice to avoid numerical mistakes here. And for these checks, I would recommend, like triangle test is probably one of the most prominent ones. Please look up online a suitable algorithm. For many, you can even find implementations. These we will not discuss in detail, but we'll focus on the steps before, where we kind of have to build data structures and algorithms that quickly yield us the pairs that we want to check. And along the way, we'll actually look at some related tests, but things like these triangle checks and potentially other primitives that you might want to test. For that, I would refer you to the literature. Yeah, so much for the overview. So, what's the goal of the broad phase? The main goal here is to cull, to remove as many of these pairs as possible without skipping any collisions that would really happen. So that's really the informal summary of the broad phase step. And yeah, let's look at an example to illustrate the challenge here. This is a nice case for collisions. It's actually quite a challenging one because we have all these tori, which are in a way simple shapes, but because of the opening in the middle, and these actually have sharp edges, this is already quite challenging. And then we have a lot of them. I think in this example it was almost 1,000. I'm gonna play it again. Yeah. And then actually also these sticks that they're falling on, this is quite tough for a collision detection step because they're relatively small. So this is challenging. And right, given n objects, how many tests, worst case, do we actually need to perform? What is the complexity here of the step in terms of collision pairs? If you think about it, this is essentially n squared, right? We have an n squared complexity because every object, every one of the n objects could collide with every other of the n objects. If you're looking a bit more closely, it's actually symmetric, right? If object A collides with B, we don't need to check B for A because this is a symmetric relationship. We only need to check each pair once. So hence we can do the famous formula that it's n times n minus 1 over 1/2 tests. And that's still on the order of n squared. So it's still very expensive, right? So key challenge of the broad phase is we want to avoid the n squared complexity. That in a way is all that we're dealing with in the following. But right, it's actually not simple. As you can see in this example, we can have arbitrarily complex situations, and we need to avoid that we discard two of these objects and say they're not colliding when they actually do. Right? This is in a way the key challenge. But beyond that, we want to remove as many as possible of the non-colliding pairs so that we have as little work as possible in the narrow phase. Yeah, so let me give a quick overview of this collision detection chapter. So first I want to discuss what's broadly known as culling algorithms. So these are steps in the broad phase that quickly discard many of these pairs. Then in a way is a variant of that, but because it's a larger topic as a separate one, I want to talk about bounding volumes and then also how to work with them in terms of hierarchies. So this is going to be the second potentially largest chapter. And then we have a third one on spatial partitioning, which is related as you see, but there are actually some interesting differences in there. So for this part also I want to focus on I already dealt with the introduction and now I want to focus on these culling algorithms. And there are some other variants here, but I just want to discuss two in a bit more detail to give you an overview of what that could look like. And the second one is actually a bit special as you see, but in a way the point is a bit to show you what's possible at this stage. All right, so let's look at that again. We have different objects or primitives. We can always kind of distinguish the granularity if you want, so the scale at which we want to detect intersections. And here in this example now, let's consider an object A that is made out of n primitives. Those could be spheres or triangles or so, and another object with m of them. And then, the brute force variant would be that we test every one of the primitives of A against every one of the ones in B, giving us an n times n complexity. And now one key assumption, it sounds a bit stupid potentially to spell this out, but this is actually crucial. I'll get back to this a few times. A key assumption is now that many of these primitives that we're testing are actually far away from the primitives in B. This is crucial because if we cannot make that assumption, that means that all of these primitives are actually close together all of the time pretty much. Then we actually don't need to spend a lot of time discarding pairs because they're just very close all the time, so we probably need to test them. If we could not make this assumption, we would basically have to work only with a narrow phase and just test everything against everything with an n-squared complexity all the time. But we know from reality also, right, in the spaces we are typically dealing with as humans, we have empty space. Objects are typically actually not just close to each other or colliding all the time. And hence, this is actually a very good assumption that holds in many situations. Hello. All right. So, that. And now these collision detection algorithms inherently rely on discarding the pairs that do not collide. The first one I want to discuss here is this sweep and prune algorithm. So here it's actually in a way a very simple one, but nonetheless a powerful one. So we're using axis-aligned bounding boxes, meaning axis-aligned rectangular regions around the objects. They are very nice because we can very easily project them onto an axis by simply discarding some of the coordinates, right? If we want to project along z, we just discard the z-axis, keep x and y, then we have the projection onto the xy plane of one of these AABBs. That gives us intervals that we can sort and then deal with. And right, if we're already along an axis, we can very easily check from these intervals where some of them don't overlap. And if they don't overlap on an axis, then we actually don't need to check for collisions. Hence, we only afterwards left with pair tests with a narrow phase check for those objects where the intervals did overlap. Yeah, and right, this is now the right. This is already the main overview that I have here, illustrating that. Right, so if we pick any one of these axes, any one of these AABBs, for example, the blue one here, and we're projecting this onto the, in this case, y-axis, meaning we're discarding x. Then here for the blue one, we actually get this interval. For the green one, we get this interval, right? And these actually overlap. In this case, that also actually is for a case where the objects are intersecting. But I'm sure you can imagine, right? Here, if we look at the black one and the yellow one, those also would on the y-axis overlap, but they are not really intersecting. There's a clear gap. So for the green and blue one, we actually find that they would overlap on all axes, x and y in this case. For the yellow and the black one, we actually would find that their interval here has a gap in between. And this is actually already, in a way, a key insight for collision detection. If we find any direction from which we can separate the objects at any angle or any way to basically put something in between them, that means they're not colliding. Because if some free space exists between the object from any direction, that means they're separate, right? I found a space that's empty in between the object, hence they cannot collide. And for this pair, yellow-black, if I project them onto the x-axis, I can actually directly discard those two as a pair. They definitely do not need to be checked. However, in this case, I would actually record a pair for blue and green because those two seem to be colliding, at least as far as we can tell based on their axis-aligned bounding boxes. The internal shapes might be differently and might not collide, but here we can only check up to the level of these axis-aligned bounding boxes. Yeah, let's look at the complexity here, at least roughly. So if we think about it, the overall complexity of this algorithm is actually an n log n step plus another overhead of k, and the n log n comes from the sorting, right? We have n objects, hence we also get lists of n intervals along the coordinate axis. Those we need to sort, which has a complexity of n log n. So that is one step. We have multiple x's, but that's just a constant factor. So that actually does not matter. And then the k in this case denotes that we afterwards actually have to record and store the pairs that intersect. That is another step that potentially does some work, right? And here in advance, we don't know how many of these pairs we have. This could actually be a worst case, right? If we don't have this far away, if the assumption was bad, this could be n squared. But if this assumption was a good one, then typically k will be much smaller than n squared. And in a way, right, we cannot get around collecting these pairs. That's the whole point of it. So in a way, all of these broad phase steps will actually have such a additional complexity for reporting the pairs. As an outlook, you can move this into O of n for the sorting if you track these over time and then only locally update the lists as these SSXs, AABVs kind of shift around its base. But there's an insertion sort algorithm for this, so we could reduce the complexity here a bit more. But yeah, this is the overall view of the expected performance for the sweep and prune. And yeah, important to keep in mind, this is just the first step. Afterwards, we need to go in and either maybe look at the parts of these objects contained in each AABB or do the narrow phase pairwise checks. So this is inevitable afterwards. I think the sweep and prune is very intuitive. We'll actually get back to a variance of that for the bounding volumes. Now I want to talk about a very different approach to show you what is kind of possible in these broad phase steps. So as mentioned here on the slide, this is a much more specialized one, as you'll see. So this collide algorithm is based on visibility. So it's a bit related to what I just mentioned with finding a gap between objects. Here we kind of rely, or we try to find out whether we can look at these objects in a way that some objects are completely in front of others. So previously for the sweep and prune, we actually try to find gaps along a coordinate axis, so basically a slab along some axis, XYZ, that separates the objects. And now we would like to find a viewpoint where some object is in front of others. And yeah, if we look from this direction here, it's clearly not, right? So these blue objects overlap, but in this case it's quite easy to see. If I look at these objects from this angle, then the orange one is completely in front of all the others. And this property I can now make use of in the rendering pipeline, where we typically can quite easily check whether an object was actually drawn on screen or not. And hence, if I find a viewpoint from which I can draw an object without intersecting any of the other geometry, then I can be quite sure that this object is not colliding with the rest of the scene. And that is closely related to depth buffers. I hope you also remember those from the previous game engine design lectures. So the depth buffer just gives us the depth into the scene. It's typically increasing, right? So here's a, I think it's a Dark Souls scene, where some parts, this shield, for example, is very close, has a low value, close to black, and the other bits in the far distance are typically normalized frustum, have a value towards 1, and then it gradually increases along the distance here towards the back. And you can imagine, if I now draw a new primitive, a triangle, so into the scene, typically the depth is stored along with it, and I can compare, is the depth value of the new piece I'm drawing, is that larger than the one I already find in my depth buffer, or is it smaller? If it's smaller, it's in front, right? If it's larger, typically the shaders and so on are not even executed because it's not visible. And that's exactly what we can leverage, make use of to check for collisions. So that's the idea. And now I hope you can, let me go back to this picture here. You can see where this is coming from. What I can, for example, in many cases quite easily do is, if I use my camera angle for these checks, I, in most cases, have to visualize the scene anyway. I want to look at it in real-time applications. And then I could try to combine that with a collision detection algorithm by tracking object IDs together with the depth test in order to track for which objects, while drawing a certain object, whether it passed the depth test or not. And then I can, from that, build at least a rough list of potentially colliding objects, and hopefully I can actually discard many of them because they were drawn without any collisions. So in practice, it's slightly more complex. I don't want to go into details. Actually, you can find the paper for this algorithm online. We actually need to, in a sorted way, first, I think you typically need to draw the back faces of the objects first, and then in another pass draw the front faces, so that we can really make sure that all parts of the object are covered, and they need to be drawn in a sorted order, because if I don't sort, and I would draw this object first, then, right, if I actually I just draw front face of this object, then I would skip all of the parts hidden behind it, right, all these parts of the other objects, and then I potentially would not even get the correct depth values for these faces to test them against the backside of this object. So there's a slight additional complexity here to make this work, which doesn't matter here. I just want to give you the overview that it's possible to use the or kind of misuse the rendering pipeline to do collision checks and to discard non-colliding pairs. And from this angle, I think this collide algorithm is actually an interesting variant. But right, I don't want to go into detail here. This is really just meant as an example. Right, you can basically be creative. You can use any means at your disposal to discard objects that don't collide. We typically have to visualize a scene anyway, so if we can reuse information there, why not? I think it's an interesting alternative. Yeah, and that's already the end of this culling and overview chapter. And then in the next one, we're going to look at bounding volume hierarchies in a bit more detail.